We're discussing kSVD for sparse signal representation. And kSVD is an iterative algorithm that involves two steps. And when we talk about the kSVD algorithm, we're talking about learning a dictionary and a representation that will enable us to use as few dictionary elements or atoms or vectors as possible to accurately represent the input data. Once we have the dictionary learned, then kSVD to represent new data actually simplifies down to just the first step, which is the sparse coding. We went through the sparse coding step and found that there's nothing real magical about it. It just essentially involves marching through the dictionary, checking out each one and seeing what provides the best fit for any given data sample, using it, and then finding the next one that provides the best fit to the residual after we've matched the first element. So I should have made a notation change right here and indicated that we're operating on our updated Y iterated approximation. Okay, so that's step one. Step two, coming up with a dictionary dictionary that best does this. This is where the real innovation or magic of kSVD comes in. And the basic idea here is I apologize. OneNote crashed, but I'm back. Okay, so we have step two, where we're trying to find the dictionary. So our scheme is goal dictionary update. And the approach is update each atom or column of D one at a time. And so we'll do this by first fixing all columns of D but one, which will be dk. And then we update dk by optimizing our original target function, which was y minus dx f2. So we assume we already have x. We found that in the previous step. So here's how this plays out. We have y minus dx is going to equal y minus the sum j equals 1 to k dj gj transpose. And for Frobenius norm squared, that's going to be equal to y minus the sum from 1 to k with j not equal to our little k. GJ transpose minus DK. Yeah, so all we've done is pull that out of that sum being squared. And now we'll call this EK. EK is the error when we remove our kth atom from D and all its contribution, the error term. So, or to minimizing the error, all its contribution to the approximation. So this is now going to be EK minus DK GK transpose squared. So as you might guess, these are assumed fixed for now. And this is the one we will update. DK. So the other thing we haven't yet introduced is this quantity here, GK. GK transpose represents the kth row of X. So as you may recall, the kth row of X is the one that contains the coefficients for the kth atom or kth column in D. So we're saying all of the coefficients corresponding to D of K are taken out and placed into this vector GK transpose. So another way of, maybe this will help, if X is equal to X1, X2 up to XP, that's equal to G1, G2, whoops, G2 to G capital K transpose. Okay. So we've already, this now looks like we are trying to do a low rank approximation to the error. So this EK term is going to represent the total error in our representation of all of our observation vectors, our y's. And we're trying to find the best, in this case, rank 1 approximation to that. And we know how to do that. We just spent some time doing low rank approximations to matrices. However, if we tried to find a DK and an associated G to do a rank 1 approximation of E, it's likely that it would no longer be sparse, because there would be nothing enforcing the sparsity. So what are we going to do to keep the sparsity? So keep the sparsity we only update dk using using y vectors essentially. That currently modeled using that dk. So let me come up with another way of visualizing this, because this is important. If we were to look at this term right here that we're trying to minimize, our ek minus dk times gk, because of the initial step, or step 1, we know that most of the gk values associated with a particular dk are going to be 0. So let me expand that out just a little bit. Suppose, for example, that we had our current x was equal to 0, 0, something, 0, something, 0. And we have a column for each of the input elements. And so on and so forth. One column for input element. Okay, now it's time to update the kth dictionary element. In this case, it's the third. Suppose the D3. We'll come along, we'll find that this one and this one utilize D3. So when we update D3, we're only going to try to minimize the error from those. So now we will define I is equal to I1 to IK, and let's see. Then let's define AI to be the submatrix of A indexed by I. So So to make this less abstract, in our example, xi contains only two columns highlighted above in yellow. Okay, so now we're going to, for our dictionary element update, we're going to minimize dk, or minimize over dk, and actually we'll go ahead and update our g's at the same time for that particular row. yi minus d xi is equal to, well, actually f squared. We'll just do that. So now we indeed have a low rank approximation problem, because this is now, whoops, that's an E, K, and I'm going to put, actually let's do it this way, comma I minus dk g k comma I transpose, and here the comma I refers to the fact that this is pulled from our xi and our yi respectively as we set up these quantities. So now we can do an unconstrained low rank approximation. And we know how to do that, but we need to go on to one more page to do it. So to do this, we find the rank 1 approximation to EKI to minimize our error and update dk. So to do this, we say that EKI is equal to U lambda V transpose, which we're used to doing. So dk is just equal to U1 and gk comma I is just equal to sigma 1 V1. Okay, now that we've done this, we go back and see how I was numbering these. I wasn't. Okay. Now update D and X and repeat for K equals I just say for next value of K. So back to the basic algorithm. We've now done the sparse coding and the dictionary update, and then we keep repeating those steps until we're done. So there's a paper that I will link to this this OneNote file that describes the basic algorithm as it was originally published. It's been cited, as near as I can tell, almost 10,000 times. So it's a very popular paper. It includes more details about implementation of the algorithm, as well as some examples. So in their paper, this is the summary of the implementation of the algorithm. Note that what they call XTJ, we've been calling G transpose of J in this manner. Actually, we've been using K as index there, but oh, I see. Yeah, so J or K, whatever it is, that's how this algorithm relates to what we've been discussing. We also have this example illustrates a little bit about kSVD's ability to learn structures. So paste. For this particular one, kSVD was used to learn a dictionary that represented images of faces. Then a new face was given it, and if we had, instead of a dictionary, if we'd had a basis, we could represent this new, the new face that was given to it was noisy. Many of the pixels were corrupted. If we had used a regular dictionary to represent this noisy face, it would have done a perfect job of representing a noisy face. However, if we come along and we instead use sparse coding, then we get a better result. And the reason why is when used as sparse coding, the strongest response is still going to be not to the noise, but maybe to the image, the original image itself. And so it talks about using several different overcomplete vectors and then using sparse coding where you use very few coefficients to reconstruct, and it tends to clean up the noise because the noise isn't represented as well. Details are in the paper, but the important part is that if we learned a dictionary and we do that, the reconstructed image is fantastic. And the reason why is the noise just isn't represented well with the dictionary elements. But what is represented well with the dictionary elements is the original signal, because the dictionary elements have learned the structures common in faces. And so this is an example that they use to illustrate the effectiveness of sparse coding and their algorithm, the kSVD algorithm.